A declaration from teacher Carlos focuses on Durham School. I've committed my whole calling to empowering an unequivocal hypothesis about the universe. Then this happens. The theory is being scrutinized. I embrace this challenge because it is through such investigation that we advance and make progress in science. The James Webb Space Telescope is fundamentally upsetting several widely held beliefs in cosmology that have been considered truths for a long time. Another ultra-deep field image has revealed that we have made errors in astronomy. The telescope, which was intended to uncover the first stars of the universe, is proving to be revolutionary. This new perspective could introduce a completely different understanding. Not all experts are troubled by these new findings. Many experts are welcoming these developments because it has long been clear that there were issues with our previous theories. The inconsistencies in measuring the universe's rate of expansion alone should have raised concerns for scientists long ago. Instead of rigorously questioning these inconsistencies, many adhered to outdated theories. The cosmic microwave background CMB, the oldest light in the universe, was created about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. This transformation, known as reionization, made the universe transparent to light. The CMB was first detected in 1964 by American physicists Arno Penzias and Robert Wilson. While working on new radio technology, they encountered a persistent noise coming from every direction. This discovery was initially seen as strong evidence for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their findings became a cornerstone in the history of space science. The CMB provides a snapshot of the early universe, with minute temperature fluctuations offering critical insights into conditions shortly after the Big Bang. Researchers use the CMB as a reliable indicator to measure key aspects of the material universe, including its expansion rate. Edwin Hubble had already made such measurements in the late 1920s. He observed that distant galaxies were moving away from us and that their speed was proportional to their distance, a relationship now known as the Hubble law or the Hubble constant. Although Hubble's measurements were not as precise as today's, they were groundbreaking. When the CMB was discovered, scientists recalculated the expansion rate and found it to be significantly lower than Hubble's original estimate. Later recalculations using Type Ia supernovae as standard candles provided a more accurate estimate, but discrepancies remained. These differences, known since the 1990s, suggest that there may be issues with the CMB data analysis methods or the concept of general expansion. This discrepancy, known as the S8 tension or Hubble tension, implies that our understanding of the universe may be fundamentally flawed. Since the James Webb Space Telescope JWST began its operations, it has provided stunning data that could help resolve this issue. Observations of galaxies so old and mature that their formation may theoretically have begun before the Big Bang challenged established theories. Modern astronomy now faces what is seen as the greatest crisis in cosmology: the rate of the universe's expansion, and our theories about how things came to be are under intense scrutiny. New images reveal a universe that differs fundamentally from previous models. The S8 tension has served as an early warning for scientists who adhere to old theories, but are now confronted with the evidence that our understanding of the universe may be incomplete. This realization has left many researchers concerned. To address this crisis, we must appreciate how science works. Theoretical scientists use a combination of mathematical models, observational data, and logical reasoning to reach conclusions. Their understanding comes from observing anomalies, testing hypotheses, and theoretical exploration. The term theory itself suggests frameworks and ideas rather than absolute facts. Our scientific knowledge comes from telescope images, sound waves, radiation captured by radio telescopes, and data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to split ancient light into individual frequencies and examine it in detail. It can show which elements were present in galaxies billions of years ago, their mass, and the number of stars. However, JWST's images have limitations. For example, It may not clearly observe galaxies or black holes with similar brightness due to gravitational lensing. Our understanding has evolved to consider various possibilities, often dismissing alternative explanations. New discoveries from JWST provide critical clues that could replace old theories with new insights. Researchers are grappling with these findings, which seems so extraordinary that finding new explanations is challenging. The latest discoveries are shaking the foundations of physics, causing concern among many scientists. Physics today is still heavily influenced by Isaac Newton's 17th century work. For a long time, his laws of motion and gravity provided the foundation for understanding the physical world and the universe. Newton's laws work well under everyday conditions on Earth. However, in space, his ideas required significant revision, achieved by Albert Einstein in the 20th century. Einstein's special theory of relativity, published in 1905, changed our understanding of space and time, showing that the laws of physics are relative to the observer's motion. His general theory of relativity, published in 1915, expanded these ideas with mathematical models, explaining gravitational phenomena based on the curvature of space-time, caused by massive objects like stars or galaxies. Einstein recognized the limitations of his theories and sought a unified framework without success. No scientist has yet succeeded in this endeavor. Michio Kaku, a prominent American astrophysicist, suggested that solving this issue could lead to a Nobel Prize. We need to investigate whether our understanding has been flawed or if telescopes themselves might be at fault. Dark matter and dark energy are prime suspects in this cosmological crisis. Current models suggest they account for about 95% of the universe, but neither has been definitively observed or proven to exist. It's possible that dark matter's properties have evolved over time, affecting gravity. While gravitational effects have been confirmed, it's possible that gravity behaves in unexpected ways. Certain constants in cosmology, long considered reliable, might vary slightly, offering new insights. Errors in distance measurements or misinterpretations of the CMB could also be factors. Perhaps our assumptions about the universe's origins were incorrect. In conclusion, the JWST's observations represent a major moment in our quest to understand the universe. New data may disrupt established theories, but also offer opportunities for scientific advancement. Cosmological models must be tested and, if necessary, revised in light of new evidence as we move forward. The scientific community faces a critical period of reassessment and innovation. The challenges presented by the James Webb Space Telescope's findings compel researchers to re-examine long-standing assumptions about the universe's origins, structure, and expansion. These findings may force a paradigm shift comparable to the revolutionary changes brought about by Copernicus, Newton, and Einstein. Embracing scientific uncertainty. At the heart of scientific progress is the willingness to question established truths and embrace uncertainty. The anomalies revealed by JWST underline the importance of this principle. While some scientists may find these contradictions unsettling, others see them as opportunities to refine and expand our understanding. The discrepancies between different measurements of the universe's expansion rate, the S8 tension and the Hubble tension, demonstrate that even the most widely accepted models are subject to revision. The role of dark matter and dark energy. Dark matter and dark energy remain enigmatic components of the universe, accounting for about 95% of its total mass energy content. Theories involving these concepts are essential for explaining phenomena such as galaxy formation and the accelerated expansion of the universe. However, the absence of direct evidence for dark matter and dark energy has led some scientists to propose alternative explanations. For instance, modifications to our understanding of gravity or space-time could potentially eliminate the need for these invisible components. Technological advances and future discoveries. The JWST is only the beginning. Future telescopes and space missions, such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, will provide even more detailed observations of the universe. These tools will help scientists test new theories, validate findings, and uncover additional anomalies that could reshape our understanding of cosmology. Philosophical implications. The potential inaccuracies in our current models raise profound philosophical questions about the nature of scientific knowledge. Is our understanding of the universe inherently limited by our observational tools? Are there fundamental aspects of reality that lie beyond our comprehension? These questions echo the sentiments of scientists like Einstein and Heisenberg, who recognize the limitations of human perception and the provisional nature of scientific truth. Collaboration and open inquiry. Addressing the current cosmological crisis will require unprecedented collaboration across disciplines and international borders. Physicists, astronomers, mathematicians, and engineers must work together to develop new models and test existing theories. Open inquiry and the free exchange of ideas are essential for making sense of the complex and often contradictory data provided by modern telescopes. A new era of cosmology. The revelations from the JWST mark the beginning of a new era in cosmology. As scientists grapple with the implications of these discoveries, they are likely to develop new frameworks that better explain the universe's origins and evolution. This process may lead to groundbreaking theories that replace or refine our current understanding of space, time, and matter. In conclusion, the findings from the James Webb Space Telescope challenge us to rethink our place in the cosmos. While the journey may be fraught with uncertainty, it is also filled with promise. Each discovery brings us one step closer to answering humanity's oldest and most profound questions. Where did we come from? What is the nature of the universe? And what lies beyond the limits of our current understanding? The future of cosmology is bright, and the quest for knowledge continues, driven by curiosity, skepticism, and the relentless pursuit of truth.